Hello. Good evening. This is Junichiro Horikawa. This is the live stream series called Houdini Algorithmic Life, and this is the 103rd episode for the series. And the topic for today, for this tutorial live, is to create one that you're looking at right now, which is a curved folding simulations using a freeform curve using a Vellum system in Houdini. Vellum is a physics simulation system in Houdini which can be used in SOP context. So that's the one that I'm going to use, and the one that I would like to simulate today is to create this kind of curve folding simulations. Using these notations, the red edges stands for the mountain folding, the blue one stands for the valley folding, and I'm gonna prepare all those inputs, user-friendly inputs, to create these remeshed geometry and be able to use it for a simulations for the folding. So it could be used for, probably could be used for some virtual simulations for the physical origami object, probably. I'm not sure how accurate it's going to be, but at least you could see, you could gather you could see how it's going to turn out by just providing those folding edges by yourself. And so it might going to be pretty useful for some of you if you are into those curved folding stuff or origami stuff. Okay, the input looks like this. In this case, what I'm using is these curves as a folding edge information. As well, I also have the plane information, which is the basic plane which you want to create the folding onto. Now in this case it has to be a plane, 2D plane. I did also try the 3D version, but the remeshing part is a bit too difficult compared to 2D. So in today's tutorial I'm just going to show you how to do this in 2D. If you are interested in using the 3D version as well, then maybe I can also show you that in other week. But 2D itself is pretty interesting, I think, so I'll show you how to do that. Now once you have those two informations, the plane, the basic plane, and the curve, what you need to do now is to create the remesh out of those two informations, so that you have the clean mesh which have the edges on top of these curves. Okay, so that's what I'm gonna do, somewhere around here. So if you see it carefully, you can see those edge is aligning to the curve. So I'm gonna show you how you can do this, how you can control your remeshing based on the input curve to a base plane. And that works pretty well on 2D, not on 3D. So there's another version how you can do the remeshing like this in 3-dimensional geometry. But for 2D it's pretty simple. It's just this. For 3D you gotta do something like these, which I'm gonna skip doing it for today. Now once you have those remeshed geometry, then all you need to do is to create a constraints for a Vellum. Now in this case what I'm gonna use is the close Vellum and modify the constraints created from this close Vellum constraints. What you just need to do is to pick the constraint which is used to bend these edges on the valley folding or mountain folding, and just set a specified angle of your needs. If you want to fold for 30 degrees, then just enter 30 to mountain and minus 30 to the valley folding as a rest length, and that's pretty much it. As a result, the final output you get is this kind of folding geometry. So it's pretty simple. The step itself is pretty simple. You can, if you if you are good enough on Vex geometry operations or Vellum, then I think anybody can do it by hearing the information that I have just told you. But if you guys are curious how exactly I did it, then this streaming might be useful for you. So I'll show you how I did it myself to simulate these, especially the meshing part for 2D and how you set specific constraints with the specific angles. Okay, I guess that's the main topic for today. Alright, so let's do this. So first thing first, let's create the geometry. I always do from scratch so that anybody can follow it. Okay, and let me also save this. And the base plane could be in any shape as long as it's on the 2D plane. So any, like, it could be like circle, it could be a square, it could be any kind of shape, but as a starter, I'm gonna start with the square grid. It's the most simple shape. And the important things for this is that you don't have any interior edges. If you have interior edges like these, then in terms of the grid, you can just change this rows and columns into. If you have imported some 2D grid or 2D planes from some other geometry which already has those interior edges, then you can use the by node with the remove shear edges, as well as you might also want to remove those points which is on the straight edge. So you could also use a facet with a remove inline points options to remove those points on the straight edge. Okay. Now this is one set to clean up the input geometry, input mesh. Okay. So this is one input. This is the base plane that you want to work on to create the foldings, and another input you need is the actual folding curve, folding informations. In this case, I'm going to use the curve to specify those folding notation, and you need to at least provide, well, you could provide at least one. It could be either mountain folding or valley folding. If you want to mix those two, that's also fine. So I'm gonna try to create some random folding curves just drawn using the curve node, something like using curve Bezier. Something like this. Any curve is fine for now. So this is one curve. Let's create another curve for the, and I think it's a good idea to have the, like, many situations. In this case, the curve is crossing these plane, but there is a chance that the curve is stopped inside a plane as well. So let's create that kind of situations as well. What I mean is that situations like these, the endpoint is inside a plane, and there's also conditions where the curve is crossing together. That's also a condition you want to check out. And let's create two more. One another VGA. So one is the curve that is inside the plane, it's not crossing with any curve, and maybe one more. Curve is yeah, and probably having another crossing, and every curve maybe you have 2 crossings like that. Okay, so hopefully this 4 curve as an input will work in the system. So if these kind of random situations works, then I could kind of assume that any kind of curve could still work. Okay, you have numbers of curves, you have so many crossings between the curves, you have independent curve as well. Some curves are crossing the plane, some curves is inside the plane, and so on. Okay, so those situations are mixed up. Okay, and you also need to define which curve stands for the mountain, which curve stands for the valley folding as well. So let's try to specify that using group maybe. Okay, so I am going to use the group node. So let's say these two, or I'm not sure which one goes for the mountain or valley. Let's say this curve and this curve is for the mountain. So well, I could also change that later, but which one's which? Okay, so this one and this one, I would like to make it as a mountain curve. So let's merge these one together as to create a mountain group. Like that. Okay, and this one, I'm gonna set it as a valley folding curve. So merge these. Create another group, call this valley. Like that. Okay, and now that I have applied these groups to each primitive, I can now merge these all together. Okay. Now, thing is that right now these curves are a Bezier curve, so I probably wanna make it as a polyline for ease of use, so that you can use with other meshes as a discrete geometry. So let's do that. I'm gonna use the convert node to first of all convert it into a polyline. Okay, like that. And probably I might want to smoothen out these part because I was using Bezier based on the point position, the control point position of the Bezier curve. The resolution is not constant, so I probably want to make the resolution constant. So let's do that. Going to use the resample node for that. Alright, and this resolutions defines the after all remeshing resolutions as well, so I'm going to make it as a parameter so that you can global parameter so that you can reuse it somewhere else. To do that, I am going to create the null node, name this controller to have all the parameters that I can control later. Then let's name this remesh res, let's go from 0 to 1 as a range and have it as 0.2 for now, and copy it to the resample lengths. Okay, and I also want to make this smoothen out a little bit, so let's change the treat polygons as subdivision curves. Okay, or interpolated curve, whichever is fine. Maybe interpolated curves is closer, so I'll use interpolated curve. Okay, so that's good. I'll make these as a group. So this is the plain input. Let's create the null node so you know where to input the necessary information. I'm gonna color this to purple, and I'm gonna name this mountain curves, valley curves. Okay, so those are the information that I need in order to create the folding information. So you have a plane and a curve. Now, now that you have those informations, what you need to do now is to create a constraints for the Vellum out of these information. But in order to create a constraints, what you need is a mesh geometry. Okay, and in order to remesh the geometry to have tons of triangles and edges, the easiest way is to use the remesh. But the problem of using this remesh node as it is that the way it creates the remeshing is pretty much uniform. Or you could also use adaptive, but it's not really controllable. It's pretty much based on the curvature for adaptive remeshing. So, but the things that I really need is that the edge of these remeshed geometry is being aligned with these input curve, so that I have a clean folding edge as an input, so that I get the clean output as a simulation result. Okay, so what I want to do here is to have a controlled remeshed geometry based on those curve information. So how do I do that? That's the question. And I have searched, or I have tried all sorts of stuff in order to see how I can create the clean remeshing using these curves as a constraints, and I think I found one way to do that, so I'll show you how I did it. Now, before doing that, I do need another information before doing the remeshing, that is to define where these curves have the crossings. For example, if you have a crossing between the curves like this point or this point, you have a chance that this curve might be a mountain folding, this curve might have a valley folding. So the intersected point have both conditions for the it's going to be used for the mountain folding as well as the valley folding. So what I want to do is to set those information, store those information where exactly where the point is crossed, to store the mixed folding types. Okay, so that's what I would like to do first before doing the remeshing. So let's see how I can do that. Okay, so first thing first, I probably also need to know especially for these curve which is going outside a plane, I would also need to know where it is, where is the point which is on the edge of the plane for each curves. So for this curve, this is the point which is intersecting with the boundary of the plane, as well as these points for this curve and this point for this same curve. Okay, so I also need to know those points information as well. So let's have all those information, the intersected point information from these information. So first thing first, what I'm gonna do is to get the, let me delete this remesh. Let's get the boundary information from this input plane. Just gonna use a polypath, which will create a curve outline. And let's also use fuse node to fuse the duplicated points. So, well, maybe I didn't really need it. Okay. Now, so this is the outline, this is the curve. Let's see. In order to create the calculate the intersections, I would like to do the intersection test one by one for these curve. So I'm going to use the for each curve, for each primitive to create the notation. So using this for each primitive, you can iterate 4 different curves one by one inside this loop. Okay, now first thing first, let's try to calculate the intersection between this plane and each curve, okay, by using intersection analysis. Okay, so this one didn't have any intersection, probably. No. So let's test with the one that has an intersection, so probably this one. So this one has 2 intersection points. It's good. And I don't really need output, I just need the point information, so have that as it is. As well, I also would like to check if this curve is intersecting with other curve. Okay, so in order to check that, I need to get the curve information other than this curve itself, which you can get that by, for example, using delete node to connect it to the base input, in this case this resample node. And then set the pattern with a iteration number coming from the detail attribute for this meta node. If you look at the detail spreadsheet, go to the spreadsheet and view, look at the detail attribute, there is an iteration value which counts up from 0 to 3 in this case, since you have 4 iterations. So I can refer to this value so that to this pattern for the delete, so which geometry should be deleted to get the rest of the curve. So let's access those information from for each begin metadata iteration, and you get the rest of the curve. Now you'll be able to get the intersection between yourself and the other curve using the same intersection analysis. So in this case you have 3 points as an intersection points. Okay, now you have all the intersected point information. Let's merge these together. Okay, and then let's make sure that these points are touching on top of the curve, since the intersection analysis tolerance will make the intersected point being offsetted a little bit off the actual intersection point, so there is a chance that it's not actually on top of the curve. So to make sure it is on top of the curve, I am going to use the ray node to the original curve with the minimum distance option. Okay. And let's make sure the point is on top of the curve. Yes, it is, I think. Let's check with this null node. Yep, I think it is on the... So if you look at the one before using the ray node, maybe it doesn't really change visually. So probably this operation might not be necessary, but just in case. I think I added because I needed it for in order to use the really small resolutions for the remeshing later on for more detail. So let's make sure I have this. Okay, now next thing I'd like to do is to and maybe, well, yeah, one thing I forgot to do inside this ray node is that I would like to get information in which address or which UV positions you get out of for those points on the curve. So if you look at these curve, the UV of this curve is going from 0 to 1 from the start position to the end position. Okay, so each point has the UV information. If it's on the half position of this curve, you should be able to get the U value as 0.5. In those points, maybe 0.2 or 0.25 or something like that, maybe 0.4, 0.7, 0.8 or something like that. I would like to have all those informations out of these points, and in order to get that, the easiest way is to use this ray node, which you can get the UV value by checking this value, I think, hit prim UV. And if I look at the output geometry with the information, there you go. If you look at each point which is touching on the curve, you get this hit primitive UV. This shows that which point is each point positions shown as a UV value on top of the curve. So each one has the actual address on top of the curve. So by reusing this later, you could specify these positions on top of the curve by using this U value. Meaning you don't really need to hold the point geometry anymore. You just need to, you can just have those numbers to recreate these point position. Okay, so that's good. Now, but I do okay, so now the problem is that UV value is in vector value right now. So you have X, Y, Z value, but you're only using X value, which is the U value, because this is a curve. You have only one-dimensional information. So let's just get this X value out of this UV vector and apply it as a float attribute, just copying the X component You could probably use attribute promote, but I'll use the vex way. So the name is hit prem uv, so I'm gonna create the float attribute called u, named copied from hit prim uv dot x. Okay, let's check. So you have u float value copying from hit prim uv x component. There you go. Okay, now that you have those points with this u information, what I would like to do now is to actually create this point, the actual point that has been created as an intersection point, inserted into a original curve. So if you look at the original curve, there is an intersection, but you actually don't have that point positions on top of that curve. So what I would like to do is to insert this intersected points to this original curve as a new point, so that it can be used for a remeshing. Okay. It can be used as a constraint point position as a remesh for a remeshing, because you don't want to move the intersection points based on the remesh. You want to fix that point position to have the best result. Okay. So in order to do that, the best way is to create add these intersected point to the existing curve. So how do we do that? I'll use the vex way as always. Now, first thing first, let me see how I can do this. What I'm going to use is, first of all, a primitive wrangle connected to a original curve, and connect this promote the points, intersected points list, which has u value. These are the points that you want to insert, okay, to the second input. And it might make more sense. It might make my life easier if the u value is sorted out from small to large. So let's use the sort node to sort out the points based on this u attribute. Like that. Like this. Okay, looks good. Now, now, what else do I need? So now that I have the primitive wrangle and the u value, I think I am ready to create the intersections, but I think I am missing one thing. What I need to know is that I need to use this u value in order to specify in which position I need to add the point. And in order to insert the points, you always have a point on the both sides. If you want to insert the point in this positions, you have the point on the previous position. You also have the point on the next positions. So it's always, when you insert the point, you always going to insert in between some line, okay, line segment. So I think it makes sense to get information in what is the previous point position, what is the next point position, so that you can insert in between those 2 points. Okay. In order to do that, you need to know in which segment these intersected u value can be inserted. And in order to do that, you need to know each point u value on top of the from the original curve. So let's have that information as well. Let's store the u value for each existing point position. Okay. Now to do that, let's see what's the easiest way to store this u value. Probably one example is to use the resample node without actually rebuilding the curve by unchecking this maximum segment length, which keeps the original segment information. And instead, I'm going to turn on this curve u attribute and change this to u. As a result, you should be able to get the value from 0 to 1 for each point positions. Okay, that's one way. But thing is that I'm not really sure this u value corresponds to the one that I get from this ray node. So in order to make sure that this u value corresponds to the ray node stuff, I would like to do another way. Use the same ray node for the curve, and for the collision curve, for each point it's going to go to the left hand side input. For the right hand side, there's a curve input. And just to do the pretty much the same things, you are just calculating the minimum like ray positions by yourself, from yourself to yourself. So the actual point position wouldn't change, but you do get this hit prim UV as a result for each point. And let's see how it goes. And there you go. And what I would like to do is to compare this u value, hit prim UV value, and the resample curve u value, and see if it is the same or not. I'm just gonna copy this one. So, and let's name this u2, and also connect this to resample node to get u1, and let's compare two values. And looks like the value is the same. Yeah, everything is the same, looks same. So I guess you could use either way, resample way, a ray node way. Maybe resample is easier. You don't really need to connect this kind of a you don't really need to have two inputs, so let's just use the resample. Okay, now let's rename this back to u. Now let's see. Now that I have this u value for each point, I can now test out where exactly this intersected point can be placed for each line segment, in between which line segment. So let's do that, shall we? Okay, now in order to do this, first inside the primitive wrangle, I am going to get all the point list from the primitive using prim points. Alright, then use the for loop to iterate all the points. And inside this loop, what I would like to do is to get the line segment information so that I can check whether the intersected point is inside this line segment or not. So PTS minus 1. The number of line segment is the number of point minus 1. So this is why I did a subtraction here. And okay, now PT1 is equal to PTS I, PT2, PTS I plus. So this is the next point. So it, oops. If I is currently at this point, then I plus 1 is this point. So you're looking at the point 1 and point 2. And I want to check if the point information coming from the second input, this U value, is within this line segment or not. So in order to check that, you need to get the U value out of those point information which you have created from this resample node. So U1 is from the point 1 primitive points. You want to get the U attribute from PT1, U2, PT2, right? Okay, now it's time to check if there's a point within this U value. Now you have a bunch of intersected points from second input, so you also need to loop through these points in order to add additional points. So create another loop. And loop and with the number of second inputs, second point numbers. Then get the U value from the second inputs. So PTN coming from the second input is actually N, so the UN coming from the second input is, let's call NU. Okay. It's a bit hard to recognize, so U and capital N. Okay. Point from the second input, you want to get the U value from N. Alright. And here's the condition. If UN is more than U1 and UN is less than U2, that means the intersection points in between is in between these line segment. That's the point you want to actually add or insert. Okay. So then those case you want to create a new points for the insertion. So but in order to do that, you do need to get the point position where to add the point. So let's get that point position. You can just use the point position of this intersected point itself, or you could recalculate the point position from the curve for more safety. Maybe the later to get the recalculate the point position by the U value might be better, so let's do that way. So in order to do that, I'm going to use the function called primuv to estimate the value, estimate the point position from the attribute inside the points. I could use either prim UV or UV sample, but in this case, since I'm using the UV value created from ray node, which is the actual curve UV value, I could use prim UV. If you're dealing with the custom attribute, then prim UV might not work properly. So in those cases, you might want to use UV sample, but if you're dealing with the actual UV, this is fine. Then get the point position, and you are looking at yourself as a curve. Then the UV must be provided as a vector, so UN 0, 0. Okay. So this should give you the point position where the intersected point is. Now it's time to add the new point. Okay, this is the new point, and let's check. Okay, so this was the intersected point. This is the newly created points. Now the point position looks good. Now the problem is, how do we actually insert this point in between these line segments? Now that's the problem, because right now it is not really connected to the primitive. This point is being separated, created separately. So in order to make this point as a part of the segment, actually you need to recreate the whole primitive from scratch. Now that's a bit of that's a bit of lot things to do. Sounds like a lot of things to do, but that's how the primitive creation works. So meaning we have to delete the original primitive and recreate the new primitive polyline based on the new points. Okay, and that's what I'm going to do. Okay, so to do that, first I'm going to create a primitive, new primitive, calling add prim with the polyline. Now currently this is empty, and inside this loop, first of all, what I would like to do is to add the first point position. So as soon as I get the point 1, I would like to add this point as a vertex to this primitive. Now next come the intersected point, inserted points. So when this condition meets, I would like to insert this point to this primitive as well. Right? And after that you could wait for until the end, and then you are messing with the last point. So in the last loop you want to add the last point to geometry, or last point from the PTS list. So maybe you could do that outside the loop by saying you want to add the last point coming from the PTS, which is the last point. Oops. Now you could remove the original primitive to check if the new primitive has these intersected points being inserted. Okay, let's check. Let's save it and let's select this point. Try to move this. And there you go. A new segment has been added to the point. Where else? So this is another intersected points, and let's check if this point is on top of a primitive as an inserted points. Oops. Where'd it go? Oh yeah, this one. Oh, yeah, so looks good. The point has been successfully been inserted. Now that was a lot to do with the small, this small network, but it's pretty important for clean remeshing. So consider this is necessary if you really like the clean result. Okay, I think that's good. Now let's also create some color information to the intersected points, just in case where you know where it is intersected. So, which is not really necessary, but just as a notation. I'll make it green. So it's a bit hard to see. Maybe make it yellow. It's not really easy to see. Maybe red. Yeah. So this is intersected points. Let's also apply some point group. I might going to use this later, where at which point is intersected or not. So I'm gonna make this intersect. Okay. And since this is inside a loop, if you connect the last node to the for each end, you do the same process to each curve, and you should be able to get the similar result. You get the intersected edge, intersected points inserted on the edge, like this. You have the intersected connection between the curve. Now why do I have this color? Oh yeah, this is on the grid, I guess. Yeah, I don't see the color on this curve, so let's check that later, as well as this curve. So there might be something missing. Okay, let's check. So what I would like to check is this long curve, and I don't see a color apply to this curve. So let's see why. Which one is it? This one. Okay. Now, yeah, I don't see colors. Wait a minute. Okay, something's wrong with this one. Okay, this is yourself, but I'm including yourself as a excluded curve, so that's a problem. Why is that? Why this happens? So wait, which number is it? The iteration is 3. Okay. And what I'm deleting is hopefully this one. Let me check the primitive numbers. It's a bit too small. So this is 3. And why am I not deleting this one? but instead deleting 0. I'm not sure. Not really sure. Okay, instead of using primitive delete node, I'll try to use the primitive wrangle instead to see if I get the different result. I'm gonna connect the iterations like this. Basically, I'm doing the same thing. I get the iteration value from the second input. And if the primitive number is equal to iteration, then delete that primitive. Okay, this works. So maybe something is wrong with this expression. Somehow. Not sure. Well, since this one works, I'm gonna get rid of this one. Okay, going back to the final result. Let's check. Okay, that looks good. That looks good. You have colored. Now this one doesn't have any crosses or intersections with anything, so no red points. Okay, everything looks good. Now, this is a preparation in order to check which point is being intersected or not. And also refine the curve so that you have the connected points to share the remeshing points. Okay. Now this part, I think this part is pretty somehow important, you know, if you would like to get the clean mesh or clean result for simulations. Now that I have prepared all those curve, it's time to actually remesh create the clean remesh geometry based using this curve as a constraint. So let's do that. So first thing first, what I would like to do is to remove the points from these curve which is outside the plane. In this case, this part is outside the folding plane. This part is outside the plane, so let's remove those informations, which is because these are not necessary. So I might not need to do that, maybe. Well, yeah, I might not need to do that actually. Let's try to avoid that. Let's try avoiding deleting that and see if it's gonna work without deleting those outside points. Okay. First of all, to tell you the overall steps how to create the remesh, this is how it's gonna work. First of all, I'm going to create the extrusions with these curves to a normal direction of this plane. In this case, normal direction is y direction. So create the extrusion to the y direction for each curve, which will create the wall-like shape. And next I would like to create the Boolean intersection between the plane and the extruded plane, extruded curves, which will create some edges inside the plane. Okay. And using that information, using that mesh by using the remesh node, since remesh node will not move the boundary points, and where you have intersected between the extruded curve and the plane mesh will going to be the boundary points for resulted geometry. So by using the remesh, since remesh doesn't modify the boundary point positions, you get clean remeshing by preserving those curve point position. Now it's easier to do it by saying it, so I'm just gonna show you what I mean by that. First, I'm going to create the normal directional information to each point on those curves, because I want to extrude it on the normal direction, in this case to the y direction. So create a n attribute, which is the normal attribute, and value as 0, 1, 0 for vector. Now you get the up vector information as a normal direction to each point for this curve. Now after that, I'm going to extrude these curve using poly extrude. The length doesn't really matter, maybe it could be 1. And the direction that I want to extrude is the upward direction, so I'm going to refer to the point normal existing, which will create this kind of a strip-like extrusions. Okay, and what I want to do next is to create the intersection between this ribbon and the plane. So I think it makes sense to move this strip a little bit, go negative y direction. So maybe the half size of 1, meaning 0.5 minus 0.5, moving to the negative y direction. So let's copy this distance, paste it to the translation, and say multiply by minus 0.5. Okay, this will create the intersection between the strip and the plane. Okay, now let's do the Boolean operation between the actual plane. Now in this case, the actual plane must be a must be the one that has a face. So I'm gonna use this one. Let's create the null node. Let's call this base plane. Somewhere around here. Let's use the object merge to refer to this base plane. And let's color this to yellow so that I can see this one and this one has some link. If you really want to show the link as a visual, you could go to the view node, check show for selected nodes. You can see that there is a connection between these two. Right, so what I want to do is calculate the Boolean between this plane and this surface, the strip. And the way I want to calculate the Boolean is important. What I would like to do is the Boolean between the surface and surface for sure, and also I would like to calculate the subtract, so that's good. And a minus b, that's fine. A is the plane, B is the strip. Other than that, I think that's fine. And I think I do need the intersected edge group information. So I'm gonna get this AB seams information where there's intersections between the geometry, the plane, and the curve. So So these part should be the curve, the edge, which has this AB seams. And if you visualize the points, you could see that the output geometry out of this Boolean node contain these point information coming from this seams. Now this is important. Okay, that looks good. Now's the part to actually do the remeshing by preserving these points. Wait a minute. Preserving these points and try to remesh by preserving the existing points and create a clean meshing. To do that, I'm going to use the remesh node, and you just need to connect this as it is. And for the target size, I'm going to use the same size that I use for this resample node. So I'm going to copy this 0.2 to this one. And let's also make sure that I have enough smoothness, so I'm gonna make the iterations pretty big, right? Like that. And as a result, maybe you cannot really see what's happening here, but if you visualize the original curve, which has been used for the folding, and compare with the actual remeshing, you see that you are getting these remeshing along with these curve. See? Now that's really clean. Now there is some small edge problem here, so might need to fix that, but other than that, it's pretty clean. So that's one thing I found out throughout this tryout. In order for 2D meshing, this works pretty fine. Okay, so and in order to fix this part, maybe I might need to relax this point distance between this point and the other points. So to do that, maybe I could use something like smooth or for the curve, or the smooth for the actual remeshed geometry. So either way might be fine, might work. Not sure which one's fine. I think I haven't tried that. So let me see if I can go with the curve smoothing first. See if it's gonna work. So this is not the things that I have tried before, so not sure if it's gonna work. But let's see. For example, if I want to use smooth and to this point, and obviously the constraint points will going to be the intersected points. These are the points which you don't want to move. So let's compare the result. Now if you look this point positions carefully, if you set this to 0, this is the original conditions. If you increase the iterations, you're seeing some point separation between the constraint, the intersected points, and the next points. Although the problem is the curvature of the whole curve is also changing, which might not be ideal. Right, so might make more sense if I can have some kind of attribute weight to those points which is close to the intersected points, and based on those weights, you can control the smoothness. Maybe that might make more sense. Now, I'm not sure if I can do that with this smooth node. Let me look at the help. Constraint points, attributes, strengths, how much? It looks like the strengths applied with this smooth node is kind of uniform, so maybe it's not really possible. Okay. So what about attribute blur? This has the weight attribute, but this doesn't really work with the curve, I assume. Let's check. Now this doesn't have a constraint option, so I guess you need to set the weight by yourself to this intersected points. But let's see if I change this. So this doesn't really work with the curve. I think I need to turn this off. Okay. So let's try with this attribute blur. First of all, I need to create the weight to each point. So I am going to use the point wrangle. Alright, first thing first, if I'm gonna check if the point is intersected points or not by using endpoint group 0 intersect pt. Okay, so if intersected is equal to 1, then you don't want to move that point. You're going to assign the weight to 0, meaning this point is not going to be used for the smoothing. Okay, else, now based on the distance between the original point, current point position, and to the intersected point, you wanna, if it's close enough, you want to have the high weight attribute to have the high smoothing. If it's far away, then you don't want to actually smoothen out anymore. So you want to calculate the smallest distance, the closest distance between the current point position and to the nearest intersected points. To get the nearest intersected points, I could get the intersected point positions somewhere. Maybe I can just get that by using int function called near point, looking at yourself. So there is an option where you can specify the point group, so 0 intersect current point position. Okay, and you can now calculate the distance between the closest intersected point position and yourself, like that. Like that. And I do need to create some threshold to see, well, actually the closest intersected point that I would like to look for should be on the same primitive. If in this way, there is a chance that this point is looking at other intersected points. For example, wait, maybe this point could look at this point, which is not really related if the threshold is big enough. That's not really ideal, is it? No. You only want to look for the own primitive's intersected point positions. Right. So, this filter is not enough. How do we do that? I forgot if there is a way to create the AND condition to the group. Not sure if that's possible. Let me see if I can do that. So if I use the intersect as it is, you get several points. Now that's understandable. What if I only want to get the intersected points belongs to certain primitive, like 0, primitive 0? I don't think you can use AND. I don't think that works. So, and by just adding the group to with the space, it just means or condition. Oh well. I think there was a way to do the AND condition. Let me know if anybody knows how to create the AND condition for group expression. Let me search for it. Okay, it says I don't think there is specific AND operator, but there is except and not. Right, I think I remember using this some time ago. Okay, so you could add a condition as an exception. This might works. Alright, let's copy this and let's test with this one. Each primitive, so this is the condition, intersect and not 0. Nope. Nope. Maybe the number itself doesn't work. Not sure. Well, it has to be used with the attribute. Or backslash. Nope. The 0 works. Wait a minute. Okay. I wasn't looking at the primitive. This was point. That was the problem. Okay, but looks like it's gonna work. Right. Going back to the... So you have to add the point group information. Right. So in order to make this work, you need to have each point to have the primitive number informations. Right. I'll do that. Before going into this point wrangle, I'm going to store the primitive number, corresponding primitive number to each point. Now this sounds a bit hacky, but maybe there's a better way, but just trying out. So this should be the corresponding primitive number for each point. I've just copied the primitive number to the point as a prim attribute. So this indicates the primitive number, right? And going back, and what I would like to do is looking for the nearest point which is on top of the same primitive number. So, and you can only use exception condition. So except conditioned at prim is not equal to the current primitive number. So the current primitive number is I2A prim. Yeah. How's that? Now, how do I check if this is correct or not? Good question. Well, let's create the threshold. Searching distance. And if this is within this if the distance is within this threshold, let's say I would like to set the color to blue. And doesn't seem to change. Okay, so you do see some changes. Now I want to limit to a certain primitive. So let's say if I would like to only work on the primitive equal to 2, I'll just add a temporal conditions if ptnum wait. Wait. I guess just changing the color based on the primitive number might just work, right? So we'll just say I at prim multiply by 0.3 or something. If the color is different for each primitive, then that means the filter is working fine. Yeah, this is darker, this is lighter. The filter seems working just fine. Alright. That's cool. That is cool. Okay. So now the filter seems to work. It's just a matter of how you set the weights based on the distance. Let me make the threshold as variable. Like that. And then based on the distance, I would like to set the weight. So if it's closer to 0, you have more weight. You need to make these points go far away from the original point, so the weight should be bigger. If it's far away, it's close to this distance, then you should make the weight close to 0. So you're gonna use the fit. Distance from 0 to threshold. If it's close to 0, you get 1. It's close to the, it's more than threshold, then 0. There you go. Okay, now I could check it, check those weights using the color node, just in case. So from white to red. More red, more weight. Cool. Looks good. Now it's time to use those weight to actually smoothen out. Okay, so looking at the weight attribute, let's check this. Okay, not bad, but smoothing too much on the edge, so probably blurring iteration might not need to go more than 1 or 2. 2 is fine. Now let's also increase the threshold searching distance a little bit more to have more smoothing. And probably I could do the distancing. Maybe I could have the power function to this one to make more smoother result. Okay, that looks good. That looks much better. Maybe 1 or 2 is good enough. Maybe 2 is fine. Yeah. You are changing a little bit of curvature, but only somewhere around here, so hopefully this is not a big problem. Alright, that's good. Now connect this back to extrude and see the result. Oops. And looks cleaner. No shorter edge anymore on the intersected points. Cool. Alright. Now this was the remeshing part. Okay. Now what else do I need? At this point I don't need the intersected point information anymore, so maybe I can recolor it to white for now. White face for now. And what else? I might also need to fuse this, because since I used the Boolean between the face and the strip, there is a duplicated points on these intersected points. So in these points there is actually 2 points. So that's not really necessary, so let's merge these points using fuse node to make it as a clean single plane. Right. Now let's name this as a remeshed geometry. Okay. So now It's time to create a notation to this mesh. Which edge is for the mountain folding, which edge is for the valley folding, by referring to the original curve. Okay, the original curve is the one that you have smoothed out here, this one. And each curve has a primitive group called, oops, it's not this. The group is missing. Well, each one should have a group called mountain or valley, but it's being deleted somewhere. Wait a minute. Where did it go? So this, until here, this has a group. Maybe somewhere inside here, it's been deleted. This one has, okay, when I have recreated the polyline, the group has been deleted, so I need to set the mountain and valley group back to the primitive. So set prim group to mountain to primitive number in prim group 0. This will just copy the mountain group from the original primitive to the new primitive. Do the same for the valley. Let's check. Nope, nope, it's not working. Valley, mountain. Why did I miss? In prim group, valley, prim num, prim num. Maybe I need to separate this or not. I don't know. Wait a minute. This should not be primitive number, but this should be the new primitive. The one that I've created right here. Right. There you go. There you go. And now you have these curves with the smoothened curve with these mountain and valley group information. So let's connect that to a null node as well. It's this. Okay, so you have two refined geometry, in inputs. One is the remeshed geometry and one is the curve, the smoothened curve. And each one is aligned perfectly. Okay, so using those two information, I'm going to attach or set a edge group to the mesh, whether the edge is for the mountain folding or for the valley folding. Right, simple as that. So, to do that, I am going to use the feedback loop to loop through all the curves, and for each curve I'm going to update the remeshed geometry with the updated edge group. So for each primitive to curve, and I don't want to merge the result, I just want to feedback the loop. So actually, I'm not sure if this is the I guess maybe This is not a good idea. Maybe I can just do the loop for mountain and for the valley. So just 2 loops. So I'm gonna use for each number, create just 2 loops, 1 for the mountain, 1 for the valley, right? And then make it feedback loop, because what I want to do is to update the mesh with the edge group, new edge group. Okay, connect the mesh geometry, and for each iterations, if the iteration is equal to 0, I want to get the mountain. If the iteration is equal to 1, I want to get the valley. So let's get that information, shall we? I could either use delete for, but since I have to filter it with the word or string, I'm gonna use primitive wrangle, which is easier. Okay, first of all, get the iteration from the second input. If the iteration is equal to 0, you want to get the mountain, so remove prim 0, prim number. Wait a minute. Remove prim. Can I? Okay. I think I need to create the conditions. If iteration is equal to 0 and prim group valley is equal to 1, then remove it. Else, if iteration is equal to 1 and prim group 0 mountain is equal to 1, then remove the mountain so that you can get the valley group. Like that. And let's check. So if it's 0, you get the mountain. If it's 1, okay, this doesn't really change. Okay, looks good. This mountain, this valley. Alright. Now I can refer to the original mesh, which is this one, and do some comparison with this mesh and the curve to create the edge group. Okay, shall we do that? Okay, so I'm going to use the edge wrangle. Does this have an edge wrangle? Nope. Just gonna use the attribute wrangle. And look for the edge group. Okay, so going back to the mesh, the points where you need to actually look for, the edge that you really need to look for is the one that you have this AB seams edge group, hopefully. Let's see if that's so, if that's true. I'm going to, okay, there is no edge group to color, so but there is one here. Okay, so this looks correct, right? So these are the edge which has this AB seams. So these are the edge that I would like to set the group either a mountain or valley. Okay. So inside this wrangle, I'm going to filter the group with AB seams. Doesn't have it. Does this? I want to make sure if this is working, so I'm gonna check by setting the y coordinate to 1 for the edges. Okay, looks good. Check-in done. Now it's time to actually set the information, shall we, for the edges. Okay. Now, actually, I'm not sure if I need to set the group to only to the edge, or maybe I do need to set the edge or to the point group as well. Yeah. Okay. Okay, so in order to do that, so you have these points, you have these. All the points should be in corresponding position. Right? The distance is pretty much close to 0. So, what you can do here is you can use a new point function for second input with the current point position. Get the point position just in case, and not sure if I need to do that, but just in case, I'm going to calculate the distance between the current point position and the nearest point position, and just to make sure that distance is close enough to 0, I'm going to apply a group to each point. Now, I know that this one is the mountain if the iteration is equal to 0, and if the iteration is equal to 1, then it's valley. So based on those iteration number, I need to change these information, which group that I need to apply to each point. So what's the best way to do that? I could either connect this iteration again to create another conditions, or is it possible to copy the group from this primitive? Maybe yes. Yes. So in those cases, you need to know the primitive number for this closest point. Right, so int n prim is equal to point prims 1 and pt 0. Okay, and I can get two information. One is mountain prim group from n prim. I could get another information from valley in prim group. Like that. And then if there is a if this primitive is a mountain, then this will give you 1. If it's not, this will give you 0, vice versa. So I can just copy those information, set point group mountain to the current point with the mountain information as well as the valley. Okay. And maybe it might also make sense to color based on the these information. Okay, so set point group 0 cd at ptnum. Wait a minute, this has to be valley. Now there's a possibility that one point contains one point's used for the valley folding and also for the mountain folding, especially when the point is being intersected with other curves. So I need to make sure that both groups being used for the coloring. Now how do I do that? Okay. I have an idea. Wait. Okay, I'm gonna set the color node just behind just before the for loop, and just for the AB seams I'm gonna set the color to black, like that. And going back to the folding group, and based on the mountain or valley information, I want to set the color to each point number based on the mountain and valley information. So mountain and valley. So red is for the mountain, blue is for the valley, and I am going to use this add option so that the values will be incremented over feedback loop. Now there you go. And where at the intersection point, where there is an intersection point, you get purple because you are merging with mountain and valley. Okay, seems to work fine. Right. Okay. So that's good. I might also want to set the edge group as well, so need to find the edge which is on top of the AB seams from this point. Okay, how do we do that? Let me look at X functions. So there is an expand edge group. This will give you all the edge numbers which shares the same group. In this case, seams, AB seams. So probably I could use this one, but this doesn't have to be inside a point wrangle. This should be inside the detail wrangle, right? So this is for the points, and you get another wrangle for the detail to set the edge. Now you have to refer to the same information. I don't know if you really need to have the edge group after all. Let's try to skip that for now. And if I need it, I'll come back later. Okay, so for now I have set the point group for each point. Right. Okay, and what else? What else do I need? So if I look at the output, for points, there's point which has the valley, there's a point which has the mountain, and there's also a chance that one of the points or few points are sharing the mountain and valley at the same time. Cannot find it here. Is there any? Okay, well, actually I shouldn't do this way because it's overriding the group. Right. Right. So if I want to do this way, I need to look for the current point group, if it includes mountain or not. Okay, so and just use the larger one. So just use the maximum. You don't really want to override with 0, but keep 1 is fine. So do the same for the valley. Okay. Now let's go back to the result, and hopefully I'll be able to get the one that shares the mountain and valley, but I still don't see it. Okay, must be wrong. Must be something wrong here. Not sure why. I am not sure why. In point group, mountain, ptnum, just should get the current point group. And since I'm using the maximum, I'm just getting the larger one. 1 or 0. This is point, whoops. This is point number 72. 72. 72 must have 2 groups. 72. Oh yeah, you do have 2 groups, so that's good. Okay, it's a bit hard to see with the purple, so let's color it to green. I'm gonna do it this way. Check if it contains mountain group and the valley group. I'm just going to copy this part and this part. And calculate the conditions. If both condition meets, then set the color to green. There you go. And probably might be a good idea to set another group to this position. Both. Alright. Do I need anything to do? Do I need to do anything else? I guess not for now. And looks good in terms of the notation. I have now the mountain folding information and the valley folding information. And I might also need the boundary point information as well for calculating the constraints. So let's have that using a group node. Name this boundary for point. Set include by edges, unshared edges, then you get the boundary point group. Okay, so those are the information I might need in order to create the final constraints for the Vellum. Now we came along we came a long way to until here, but it's almost done. Now you have all the necessary information to create the constraints. It's going to be the fun part. Okay. So next is finally the Vellum. So in order to create the curved folding, what I'm gonna use is close constraints, but by making the bending stiffness really big, I'm gonna make it more like a paper-like shape or metal sheet-like shape. Okay, so where's the close? Vellum configure close. Okay, so input the geometry, input the mesh to a close constraints, and you get two types of constraints. One is for stretching, and one is for bending. Now stretching part, I don't really need to change anything. It just keeps the edge lengths to be constant. Now the bending part is the important stuff here. And to simulate the folding like an origami. Then what I want to do is to set some custom angle to those folding edge where I have notated valley or mountain, and for everything else, anywhere else, you want to keep the angle to 0. So for example, if you want to for the mountain, you want to fold it like 60 degrees. For the valley, minus 60 degrees. Everywhere else, 0 degrees. As a result, you get a curved folding result. And by making the stiffness of the bending really strong, you get hard shape, more like a rigid shape. Not really rigid, but paper or sheet metal-like shape. Okay, so going into the bending, let's set the stiffness to really big, like the maximum. Scaling, just to test out. And that's pretty much it for these information. Now what I would like to do next is to change the bending angle for the valley folding and the mountain folding. So you need to pick specific constraints out of this second output. Second output is where you can modify the constraints. Now let's check what kind of parameters or attributes you have out of these constraints. You have a bunch of lines or polylines. And the one you want to look for is going into the primitive attribute. One you want to look for is the one that has bend group. Okay, and the rest length is the one you want to change. This is actually used as a rest angle for the bending in degrees. So if you set this to 30, you get 30-degree bending for the bend constraints. Okay, so that's the one you want to control. And in order to control that, you cannot change the order of these constraints because this is corresponding with the geometry from the first output. So you cannot change the order, but you just have to change this rest length by not changing the order of this geometry itself. So what I could use is primitive wrangle to modify the constraints information based on some filter. Okay. And I need to only pick up the constraint, the bending constraint, which corresponds to the edge for the folding, mountain folding and the valley folding. Right. So to get that information, before actually writing some Bex code to filter out which geometry I should look at, let's test out with the small number of geometry. Now, in the final, in the last part, you cannot really use delete because delete node will change the order of the geometry. So this cannot be used in the final output, but this is the test, just to test out, just to filter out what information I need to look for. So first of all, let's just look at the bending constraints. So these are the bunch of bending constraints. And let's also look at one of the bending constraints which is used for maybe this valley folding, where you want to bend like that. Okay, so which one will be this edge? So if even for the bending primitive, you have bunch of primitive, and if you look at carefully, if you select one, you have polyline containing 4 points crossing, and one that you want to look for is the crossing polyline which crosses over these triangles. Triangles meaning triangle that share this edge. So the one you want to look for is the polyline which connects all those 4 points in any way. So let's look for that. Which one is the polyline that I'm looking for? This is not the one. It's not the one. Not the one. Okay, this could be the one. Let's try to pick that. Okay, so this one looks like this. Interesting enough. And if you look at the geometry spreadsheet for this primitive, you have something like compression stiffness, constraint tag, damping ratio, rest length, and so on. The one you want to really change is this rest length right here. And in order to retrieve this information, you need to find some rule in order to filter out this geometry out of all those triangles or polylines. So that's the key part in order to modify the constraints. Now before doing that, let's test out just by changing one angle for this primitive. And this is from 1008, okay? So let's try to change the rest length for to maybe 60 degrees for 1008 numbered primitive. Okay, going to the 1008. There we go. You have changed the rest length to 60. Wait a minute, this is not okay. Actually, by using delete, I have changed the order, so this number cannot really used. Okay. Where did it go? Where's it? Okay, so I actually need to delete from get the value from this. So what I'm looking for is this one. This one. Okay. Then you select this one. Okay, so 9532 is the one that I'm looking for, I hope. Yup. So let's change that to 9532. Oops. Okay. And let's check. 9532. Okay. Okay, so this is the bending group. Let's see how this will change the result of the simulations. So I'm gonna create a Vellum solver. Connect the modified constraints somewhere around here. Let's check. And I'm not going to have the gravity. I don't need a gravity. I don't need a wind or anything. I also don't want to have a ground plane, so let's remove that as well. Where was that? Forces. Did it? Simulation. Where can I set the ground plane? Oh yeah, this one. So it's turned off. Okay, so let's try with these. If I play it. Okay, nothing seems to happen. If I goes closely. Okay, I do see some bending start to happen somewhere around here. Maybe the stiffness is too hard to bend with just one constraint. Let's make the constraint stiffness, bending stiffness, a little bit smaller so that I can see the effect a little bit more. Yeah, I do see some changes somewhere around here. So I have just set one constraint, but it is changing something. I've set to 60 degrees, but it's probably just around 30 or something. Maybe you need more neighbor edges to have the angles. Or I could try to set the stiffness just for this edge to make it really big. So something like that. Power of 10 by 10. That should be really big. Let me check. 9,532. Okay, so one edge will have the really high stiffness, another one is pretty small. So this makes this, only this edge will bend really strong. Let's see what happens. The result doesn't look different that much, is it? Let me change the value to 1 for overall. Okay. Now I do see start to see some changes. Well, you get the idea. Now, what I need to do now is to find all those edges, all those constraints, which is either a valley folding or mountain folding within this primitive wrangle. Now that's what I need to do, and I need to find some rule how to find that edges or polylines or constraints. Okay, so let's think about it. Going back to a single polyline. This one. First of all, let me check the point number, and 0 starts from here. 0, 1, 2, 3, so it's not in order. So that's not really useful. If you look at the vertices for this geometry, so it says 2, 3, 0, 1, so 2, 3, 0, 1, so this seems to be in the order, but the thing is that this is not in clockwise or counterclockwise, it's crossing like that. So we don't really see an exact rule here yet what this could means. So I need to think about what could be used to filter those polyline which is supposed to have this share this edge. Okay, so one thing I could think of is the edge that I'm looking for, the bending constraints that I'm looking for should have this edge shared, and also these triangles as well. Okay, so that's one way to think. The number of constraints means corresponds to the number of edges, I think. So I guess it might make sense if you have a number of edges already. I mean the edge informations already, and from those edge information I can get a neighbor triangles, 2 triangles, as well as the connecting points. So maybe I need to go back to the previous step to set the edge group after all. Right here I only had the point group for mountain and valley, but after all it might make sense to have the edge group so that I can use that information to filter out the constraints. Now that it might be the case, let's try to create the edge group. So, as I said, for the edge group, I might need to use the attribute wrangle with the detail run over, and I can use the function called expand edge group, which gather all the edge numbers which shares the same group. So geometry string. In this case, I don't have the mountain or valley group yet, so I'm going to use the AB seams edge group. Okay. Out of these AB seams groups, actually, do I need to do this inside a loop? Maybe not, because edge doesn't share mountain or valley. Edge must be either mountain or valley, so could be outside a group, outside the loop. Okay, and what I want to refer to is this curve, either mountain or valley. Okay, now for each edge found, I'm gonna loop through all the edges. And look for the closest edge primitive from the second input. In order to find the closest, you need to get the middle point position out of this edge. So let's get that. I don't use edge information that much, so I don't really know the name of the function, so I need to search for it. Edge point or edge based function. This is not a half edge, but this is just a edge. So maybe I can look for the expand edge group and returns a list of point pairs of the edges in the specified group of point pairs. Okay, so it doesn't give a edge number, but it gives you a pair of points, so maybe a multiplication of 2. So even number is the first point, the odd number is second point, I guess. I don't know. Let's check. Two. What's the best way to check? Yeah, this is okay. So you have, okay, it's a bit hard to see, but looks like so. So 0, 1, 1, 2, 2, 3, 3, 4, 4, 5. So this is the pair of points which connects the edge, which creates the edge. Alright. That said, I can change this to 2, and that means I is equal to first point. And I plus 1 should be the point to the next point for the line. Alright, so the middle point is just the average of these points. Okay, now I can look for the closest primitive by XYZ distance. And from the mid position, you get primitive and IUV as an output, and this primitive is the one that you have found as a closest primitive, and from this primitive you'll get either mountain or valley. Alright, now either one of them has a value equal to 1. So after having this, you could now set the edge group. Set edge group 0 0 okay, pt1 pt2. Alright, so 0 mountain I plus 1 with mountain. Do the same for the valley. Okay, this should do it. Hopefully. Let's check. I'm gonna use the color node. And so I think these are the edge groups because this has the AB seams. So based on those groups, I want to color it to something kind of green. If I set the mountain, it's gone. I'll set everything to white for now, and okay, I don't see any greens. Nope. What about Mount Valley? Nope. What about AB seams? Okay, so I guess something must be wrong. T. Want to make sure one of them is equal to 1. So I'm gonna create the empty array, append array with the addition of mountain and valley. So this always has to be equal to 1. And I want to check if this array contains 1 all the time. If not, something must be wrong. Oh, looks correct. Yeah, everything is equal to 1, so that should be okay. So then the problem is somewhere around here. So this is the point number which I want to add the edge group. What if I set to 1 and 1? Okay, so this is changing the color. Oh, no. I mean, I have to set to mountain. Wait a minute. I don't see any colors. Why is that? Or is it because it's sharing all the... It's trying to use the other groups. Guess I gotta use the edge. Okay. Okay. That seems to work. And why do I have these colors here? Huh. Okay. What? Make this back to mountain and valley. Okay. What is this point? Where does this come from? Interesting. Interesting, but seems wrong. I think. Right, that is the mountain. Yeah. And I'm kind of missing these part as well. This seems like these are the intersected position. So for example, if I am looking at these edges, it should be projecting to this curve. Weird. Is this wrong? Wait a minute. Okay, I know why. I have to do this way. Ah, stupid me. Yeah. I didn't use edges, the output edges. That's why. That is why. Stupid me. All right. Clean. 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 Yes. Great. Now I think I have set the edge group correctly. I'm gonna copy this because I am going to refer to the edge group again using the detail for the constraints. And go back to this one and reconnect the constraints to this attribute. And look for the edges. All right. Now, the problem with dealing with modifying the constraint is that if you look at the null, if you connect the second output with the null node, the original geometry groups is all gone. Well, it did keep the valley and mountain, but I think the point group information is gone, so you need to, in order to access the original geometry group information, you need to access from the first output. Okay, so I'm going to connect the first output to the second input of this detail attribute. Something like this. And try to get the edge group from this second input, which is the first output, the original geometry. Alright, so let's think about how do we get... First of all, I want to get the edge group, either mountain or valley. And I think I can still refer to the AB seams, which has the both valley and mountain. I want to make sure that AB seams is still available here, just to make sure. Okay, it is available, so you can still refer to that group. And then I can add additional conditions here in edge group. with a from looking for the second group, a second input, and if it's mountain or valley for edges 1, edges 1 plus I plus 1, and I also need to use 1 for this one. Okay. Do the same for the valley. Just changing the group name. And this part is not really necessary, so I'm gonna get rid of those information. Now I have some information, something like an edge information. Edge, each iterations corresponds to one of the edge, either mountain or valley, and you can check which one is it, which one is that, using this conditions or a group. Now you could get the corresponding triangle, probably using a half edge information. For example, if you get the half edge from this point to this point, the next point of this half edge, it will be this point. The previous one will be this point. So let's get that information, shall we? First of all, I'm going to create the half edge information. Half edge 1 is, how do I do that? Half edge, point half edge. So by providing the source point and the destination point, you get a half edge number. So point edge. It could be, I'm gonna refer to the second input, and then the, so I think I'm reusing these numbers a lot, so let's make it variable. Because this is a bit too long to write down. It's gonna cost my time. Okay. A bit cleaner. A bit more understandable. Alright, then half edge will be in between PT1 and PT2. So if the half edge is from this point to this point, then by calling the edge next, you get the next half edge within this triangle. I think it was in clockwise order, I think, probably. So half edge next of this edge 1 will be the point which is sharing, which is the point of this triangle. So let's call this tip 1. Now if you want to get the other way, the other triangles, then you just need to create the other way around with the different order for the half edge. So point edge coming from PT2 to PT1. So from here to here. Then if it clockwise, you get this point as a next point. So int tip 2 is hedge next hedge 2. Alright, hopefully this works. So now I have PT1 and PT2, which is this point and this point, and tip 1 and tip 2, which is this point and this point. So you have 4 points. Now you need to look for the polyline which shares all those points from the constraints. Okay, so shall we do that? And to do that, I guess I think it's not a good idea to just time-wise or efficient-wise, it's not a good idea to like look for each polyline and just calculate each point positions one by one. That's gonna be too much calculations. So instead of doing that, I'm going to calculate the centroid of the primitive and compare the distance with the centroid of these 4 points. Then if the distance is close enough to 0, then that's the one you're looking for. Alright, so before connecting the detail wrangle, I'm going to calculate the centroid of each constraints. Not this one, for the first input. And centroid can be just retrieved by accessing to add p of the primitive, I think. Let's check. I have to make sure this is correct anyway. Okay, so I have just created a centroid attribute to each primitive, this one, which should be the centroid of the primitive, and I would like to check that out. First, I only need the bending information, so let's get the bend, and let's just get one primitive for testing. Anything is fine. Like that. So you have 4 points, and this primitive has this centroid right here. Now let's try to visualize where this point is by using primitive wrangle, this one. And try to add the point to the centroid position. Oops. Okay, so looks like the centroid of this primitive is somewhere around here. Now what I'm going to do next is to get all the point position out of this primitive and get the average point position and see if the point position matches or not. So prim points 0, 0. Since I am not sure how the @p will be calculated in Houdini's Vex, so I gotta make sure everything works fine. Get the position for each point. And try to calculate the average point by creating the empty vector outside the loop, starting from 0. Add this each point position to this average point position, then divide with the number of points, and then calculate the distance between the average positions and centroid, and if the distance is close to 0, then that's good. If not, maybe I need to think about the other way. What's this? PT shadows a previous declaration. Okay. Nah. PTQ. Okay. Let's see. So the distance is, yeah, pretty much close to 0, so the average point position and the centroid is the same value. Now the check is over. I can go back here and create the conditions. I already have the primitive from the first input, so centroid is actually where in order to find out the closest distance, kind of I need to go through all the possibilities. That's like a lot of calculations, and I don't think I want to do that. So instead of doing the double loop, I'm going to try to think how efficiently I could do this without unnecessary calculations. So I have those informations, right? So first I could calculate the average point position out of these 4 points. So I have position 1, position 2. I don't have the position yet for tip 1 and tip 2, so let's get that information. Tip 1 passes and the average position is position 1 plus position 2 plus tip 1 plus tip 2 divided by 4. Right, and now I got a list of average point position, and I could probably store it as bunch of point information for the searching. Yeah, that's a good idea. So in those cases, actually I don't really need to connect the first input, but instead I'm gonna connect the constraints to the third input and make the first input empty, meaning it will create the empty geometry. Right here you don't get any geometry. And actually I wasn't really referring to the constraints, so I don't really need this connection after all for this one. What I want to do is to create the point corresponding to this average point position. So like that. And it's not creating anything. Well, that's not what I wanted. Oh, but I do get several points. Where is it? Okay, it's totally wrong. totally wrong because why am I using tip 1? Gotta use position. Okay, so these points should be the one that is the centroid of the two neighboring triangles. Shall we check that? So, what's the best way to check? So, supposed to have a point somewhere around here, but that didn't look like so. Nope, it's not. Okay, something must be wrong. Obviously. Yeah, I'm missing something. Let me go back. Okay. Let me try disabling this one and just have position 1, position 2, which should give you the middle position between the edge, on the edge. So this looks correct. Yeah, this looks correct. So obviously the tip point position is wrong. So maybe this one is wrong. Okay, I know why. The tip 1 is a half edge number and it's not the point number, so I have to get the point number out of this half edge number. That's why. Yeah, always forgot. So this is the next edge. This is the next edge number, half edge number, and the actual tip point number should be retrieved by using the edge destination point. This is it. From this next edge number. There you go. This should be correct. And tip 2. Alright, so let me check this again by making tip 1 position, add it, tip 2 position, add it, divided by 4 to get an average. And looks like we are having the nice position. There you go. So I guess the centroid of this triangle, two triangles, is somewhere around here, so it looks correct. Okay, so we can use these points as a reference to search for the actual bending constraints which shares the same centroid position. So give another primitive wrangle. Also for each point that's been created, I want to set these group information. So set point group 0 mountain to average point with the mountain information, also for the valley. And let me check. So for the mountain, I want to color this to red. Okay, looks good. What if it's valley? Looks good. Alright. Now we are almost there. Now that we wanna, what we wanna calculate is the constraints. So connect the primitive wrangle to the constraints. Then we want to refer to these points coming from the edge, and just filter with the bend group That's where we want to search for, and then look for the closest point from the second input with the current point position, and this is the centroid of the bending polyline. And if it's at the edge, you know that the distance is pretty much close to 0, so calculate the distance between the centroid of the constraints and the target points from the edges, constraint edges. And if the distance is pretty much close to 0, then that's where you want to set it as a folding constraint. So that's when you want to set whether an angle for the mountain or the valley folding. So you want to check if it has a mountain group or valley group from the search point. So in point group mountain at npt is equal to 1, then that's where you want to apply the positive angle maybe for the rest lengths. And else if in point group 1 valley, if it has a valley group, then that's when you want to set the negative angle, probably. So let's have a parameter to define the angle, rest length angle. Let's go with the 60 for now. So if it's for the mountain, set the rest length to an angle. If it's valley, then minus angle. And I'm gonna try to keep the constraints. I'm gonna keep the constraint stiffness as constant for now. So let's make it big, like that. Just changing the rest lengths for now, right? And I think that's pretty much it. Let's check. Looking at the geometry spreadsheet and look for the bending group. Okay, some of it should have an angle equal to 60, something like these. And shall we try to color these group which has the constraints which is close to 60, just to check which one is being colored, which edges, which constraint has been applied these rest lengths. So make it primitive. Okay, also I'm going to delete the attribute for the point color. Oh, it didn't have it, so that's good. So for each primitive, I'm gonna look for the rest lengths, and should be from -60 to 60. And if it's equal to 0, I'm gonna set this to white. If it's minus, make it blue. If it's positive, make it red. And there you go, looks correct. Where the mountain fold is, you get red constrained, red colors. Where the valley folding is, you get blue. So it seems like the applying constraints information worked just fine. Hopefully it did. Now connect this to Vellum solver and we are ready to check the result. And there you go. Took a lot of time to come to this far, but it's working. Yay. Okay. And you have this nice condition where you have mixture of a bending of the mountain folding and the valley folding, and seems to work okay. Alright, so now you get the system. You can now test out with all sorts of curves to see if this is generalized enough to be able to work for any kind of curves or meshes. Alright, let me clean this up a little bit. Okay, so this is the solver result. Now one thing I would like to do after this, after getting this kind of result, I don't really need these colors anymore, right? It's not, this is just for the guide. So first thing first, I'm going to remove the color by setting it to white, and now I realize that I might want to make these edges being stand out. Currently the vertex is being fused at these folding edges, so it doesn't really create this like seams. So I would like to create the edge seams to these edges. So I'm going to use the edge cusp to do that. And the group that I want to use is AB seams, which create the clean seams to these folding area. Will create more like an origami like shape. Nice. Nicely done. Alright, and after that it's really up to you how you wanna use it for like rendering, physical prototype or anything. Okay. Now I wanna test this out, if this gonna work with other kind of shapes and so on. First of all, let me try to change the base shape. Right now I was using grid, but let's see if I could use this with all sorts of different shapes, shall we? For example, using circle and try to make the similar size. Make it something like heptagonal, hexagonal, octagonal, octagon. Yeah, octagon. Switch between the planes. Let's see if this system is going to work with custom shape plane. Hopefully it does. Let's see. Okay, works just fine. That's good. Right, so next I would like to test out with custom curves, more maybe more interesting curves. I don't know what will be interesting in this case. Let me make this. Let me create another switch node. Let's share this select input. Okay. So I there was a node called spiral, so let's try to use this spiral as an input, shall we? Could be interesting. And let's try to change the size. Never used this before. Okay, this could work. So let's say this is for the mountain going over the plane, maybe. I don't know. Let's make the circle really circle. Let's make some exaggerated scene, like the edge somehow touches, something like that. Okay, let's create another spiral with some angle offset, so that you get a double like spiral seams, and one could be mountain, one could be valley. Now how do I offset this one? Yes, 180 offset. Nice. Connect this one here, connect this one here. Okay. And change this to 1. Going into the Vellum solver. Okay, the notation looks cool, good. Let's see the result. Cool. Yeah. So it's trying to keep the edge length same, so it's creating some kind of a hyperbolic shape. Interesting. Interesting. I like it. Okay, so I mean there are a lot of possibilities of this one, I guess. As you can see, you could create more like a geometrical shape like these one. You could try to create more organic shape with these setup, and this system could still work on a 3D mesh as well, as long as you could solve the 3D remeshing part, which is right here. This is the part where I was remeshing the 2D geometry to have the clean meshing based on the curve, and it's more difficult to do in three-dimensional geometry because there's tons more conditions with 3 dimensions. So you have a lot to do for that. So, but if you could solve that, you'd be able to do the same things for a 3D surface. Yeah, on top of the 3D surface, you could try to apply the bending simulations or folding simulations, just like I did here. And that could also be really interesting. Okay, so, and if anybody is interested in that, in folding simulations on 3D geometry, I could try in another week. If not, I'll just keep that to you guys. Okay. Let me know if you have any questions so far. I mean, it's been like 3 hours, so maybe I believe everybody is really tired watching this one. And thank you very much for watching till the end. Appreciate it. And if you guys have any questions, please do ask. If not, I'm gonna wrap this up and end this live. I'm gonna wait until I gather all the parameters I could set for this setup. I'm gonna gather all the parameters to this controller, such as choosing the plane, the base plane, or choosing the input curve, or folding curve. What else? Let me go through. So this was plane, this was folding curve, this was, what was I doing here? Intersection code. Recreating curves with intersections. And what's this? Remeshing, 2D remeshing. Use for constraints, and this is a folding notation to mesh. And this is the actual folding simulation. Alright. It's pretty simple. Pretty simple. I mean, I took a lot of time to explain this, but the actual implementation is not that hard, as you could see. The idea itself is pretty easy. What else? Pretty much not much parameters to set, actually. Maybe this one, but it's not really. Not really important. Not so much custom parameters for these one. It's really dependent on the input curves and input plane, and that's pretty much it. And the angle. Thank you, everybody. I have a comment from Olive. Can ask if you have any more books in the work. Also, do you think you will ever translate the Japanese only one? Yes. Thanks for asking. I am not currently writing any books for now. I probably will soon. Based on the Vex, but not now, not right now. And for the translation part, well, hopefully I would love to do it. I mean, there is a published book from a Japanese publisher, which is only in Japanese, well, also in Korean as well, but don't have an English version yet. If I guess that it's possible to publish a English translated in English book for only for an ebook, probably. So that might be a chance. That might be possible. I gotta ask to the publisher myself. Completion of this series in book form would be great. Yeah, Well, there is like hundreds of like 103 examples that I did in this series, so maybe if I could join these, assemble all these into one book, that would be really cool for me as well. That's gonna be a lot of work for sure. Yeah, but would love to. I would, if any publisher is interested in that kind of stuff, then I would love to. Yes. Okay, let me. So that's probably no more questions for this setup. I'll try with different input and just end this live. If I change the angle to something really high, like oops, previously I tried it with the 60 degrees. What if I change this to 120 degrees? Ooh, that's pretty. Whoa. Now this is nice. Maybe it's changing too fast, but love it. All right, love the result. Thank you very much for asking. Yes. Okay. Well, so this is pretty much it for everything. If you don't have any questions anymore, I would like to go to bed. Let me try a little more input curves options. See what's possible. For example, if I scale this thing minus 0.5 to the x direction, 1.5 to z direction, create the ellipse-like shape, and do the opposite for this one. 1.5 for x, 0.5 for z, and that will create some interesting cross sections. Okay, well, obviously it's impossible to like imagine what the result will be out of these curve input, folding input. So let's see what will we get out of here. Interesting. So this could be a good example that there is a curve seams which you cannot really imagine what would happen, but because of these computational setup, you could at least simulate what it would look like inside a virtual world. I'm not sure if it's possible to actually bend like this in physical world, so that's another question, but at least in logic it might work. If I animate this curve, no, that's a little bit hard to do because you are fixing the constraints before calculating the simulations on Vellum. So you cannot really like move the curve, move the constraints, animate the constraints during the simulations in this setup. If you want to do that, then you need to move this curve folding setup, or these coding here inside the Vellum solver. Right? Makes sense? And because the remeshing is based on the static curve, if you want to if you have animated the curve, then you might need to remesh on each frame, which might take tons of time to calculate and probably not be really clean as a result. But could be interesting, yeah. In those cases, maybe you need to change how you remesh the geometry. Probably. Maybe you might need to forget about making the clean mesh, but instead just deal with the duty mesh and still make this work on really small edges. But that might be an interesting topic to try out. But I know that it would gonna take a lot of time to try that out, so I'm not gonna do this for today. If you're interested, maybe another time. Well, at least you could change animate like constraints, rest lengths or stiffness inside a solver for sure. For example, you could like gradually start folding the angle for the input curve. Well, that might be interesting to try out. Can I try that out? I'm gonna go back with this simple spiral curve, and I'm gonna try to gradually raise the angle from the center to the out, or from the boundary to the center. Now that might be interesting. Okay, so to do that, I should not change the rest angle right here, but maybe I could set the rest length origin for now, right here. This doesn't really change anything, but we could refer to that information inside the solver. And we do need additional informations, the order from center to the border. So how do we get that kind of information? That's a good question. Maybe we could go back to these edge and apply some additional information to the edges, probably. No. The edge doesn't have an attribute, so that's a bit problem. So what I'm gonna do, this curve has u value, so I can copy this u value to each point, corresponding point. Which, should I do this here? Maybe. Yeah. xyz dist. Position 1 and prim uv. Now you will be able to get the u1 using prim uv. Position 1, no. Gonna want to get the u value. And like this. Right. And I could also get the u2. Recalculating the primitive and uv. Like that. And set point attriv. Now if the point is at the cross position or intersected position, you might get a different value. That's a bit of a problem, actually. Yeah, that's a bit of a problem, actually. Well, besides that, just forget about that kind of irregularity. I'm gonna try with this. Well, does the point already have a u value? Actually, it does. Is it correct? The end is 4.4, so might not be correct. Let's see. Okay, this is 0.1, this is 0.2, this is additional. Okay, let's check the point. Okay, so close to 1, so looks correct. And going back to the falling angle. So for each primitive, I would like to add additional geometrical information, which each point already has those information here, right here. Right? U value. So I guess I really don't need to do anything right here. We can go inside a solver, use something like SOP solver, SOP solver, using constraint geometry type. This SOP solver is pretty handy. You can access both geometry, the first output, and constraint, the second output. And what I want to do is to modify the constraints dynamically using this one here. I am going to copy this one here. And I probably wanna wait a minute. Probably want to set a mountain and valley group to this corresponding constraints so that it's gonna be easy to find out. I could use this group mountain and valley. So this is for the mountain. This is for the valley. Okay. Alright. Going inside here. For the subsolver, I'm going to copy this one. And what I would like to do is to access either mountain group or valley group, and then actually I don't really need those information. If in prim group 0 mountain prim num is equal to 1, or if it's inside the valley group, if it's mountain, you want to gradually raise the angle from center to border. It's valley, both same center to border but in negative direction. So based on some frame value, maybe let's say I want to gradually change the angle from 0 to 100 frames. Get set the target frame to 100. And I don't need this angle. And the current frame ratio is at frame divided by target frame. Make it float and clamp it with 1, so the minimum should be equal to 0 and the maximum is equal to 1. Right. This might be better. Alright, so you get a value in between 0 to 1 based on the frame value out of this one, and then based on this f value I want to change the angle. So fit we look at the geometry. Okay, well, I guess I would like to apply additional attributes to primitive, the constraints, which is a u value. Which can be retrieved from this first input and can be transferred to this edge group somehow. So each point has u, so you can get u1 and u2 out of these 2 points. And from PT1 PT2 and try to get the average, which will be the value of U on the middle of the line segment, and set that attribute to the point, the created point. Alright, let's check. So you have U. Let me try to color this and see how it looks like, if this is correct or not. Based on the U, I'm gonna color from red to white, and I do see some weird points here. Where does this come from? Oh well, this is kind of this is on the border, so maybe I could just ignore it because it doesn't have corresponding triangles here, so doesn't really matter about the U value for this one. And so I'm going to pass that U value to the primitive constraints, which I can do that by right here, point 1 U and PT. Right, and then pass it to a primitive. Maybe I can just do it like that. If I look at the primitive, you get UK, passed it. Then I can use that information here, hopefully. Yeah. Based on this U value plus this F, I'm gonna try to change the angle gradually. So the target angle is Remeshing's original. Which I have stored it inside a primitive attribute. This one. Yeah, there are some values called 60, so that's the target angle. Okay, and then the current angle is going to be fit F, fit 01, F, and 0 to rest target angle, and I need to use U somehow. So and the U is in between 0 to 1, so, and gradually I want to change that information. So the angle is starting from 0 for sure, and multiplying fit 01 U 0 target angle. No, it's not correct. Let me see. So How do I? What's the best? Okay. So in the first frame, everything is 0. On the second frame, you want to start you want to start folding from the center, where u is equal to 0. So right, f 0. Target angle. So when u is equal to 1, then wait a minute. Okay, I think I'm making it too complex. What I want to do, okay. Okay, first of all, I'm going to create a gradual angle based on u. So fit 0, 1. U and target like that. Okay, and or maybe I can do it like this. Right. And gradually I want to increase this value. Everything starts from 0, so minus f multiplied by okay, so when everything is equal to 1, then and you want to clamp it to target angle in the end. So let me simulate this. If f equals to 0, then you get no, that doesn't seems correct. Okay, I guess this one should be starting from negative. So when okay, sorry for making it too complex here. Starting from 0, negative target angle, by adding it using the frame number, by tangent angle, multiplied by 2. Well, how's this? I'm not sure. I am not sure, but let's see. If rest length minus angle hopefully the angle folding starts from the center and at the border from 0 to 100 frames. That's what I would like to get as a result, but let's see. Nope. It's too quick. Everything starts too quick. So, must be wrong. Let me see. Rest length origin. Oh, wait a minute. Wait a minute. Actually, I don't really need to create the conditions, but I can just use this as it is because I have already set the conditions outside. But still, something must be wrong here. Let's see. Okay, so this shouldn't be equal to this one should start from 0, so something must be wrong. So, okay, I actually shouldn't use minimum because there is a possibility that there's a negative value. That's the way, that's the reason. Right. So, in order to deal with this, first of all, I'm going to get the negativity from the original target angle by dividing self with the absolute value, which will give you either -1 and 1. Then for these target angle that I'm using here, I am going to temp target or abs target angle and replace it with these, and finally multiply it with negativity information -1 and 1. Wow, it's not really clean, but this should fix. Not really. Not really. Huh. Okay. Not really fixing it. Okay, so this is the absolute value, right? And u when the u is equal to 0, actually gotta use clamp. Clamp between the zero and abs target angle. Alright. Alright. Okay, do you see it? It's folding from the center. It's a bit hard to see. Let's color the edge and let's make the folding angle a little bit bigger, like 120. And let's carefully see it. Look from the center. Can you see it? Can you see it? Gradually folding in the center. Let's make it 200 frames because it looks a bit too fast. Okay. Alright. Well, pretty hard to see, but I think it is working somehow. It's changing pretty fast. I'm gonna make this back to 60. The edge. Yeah, gradually I am seeing the folding starts center to the border. Okay. Right. I think that's fine. Now that's one way to animate, but not sure if this is interesting enough, but at least maybe I could have shown you. I have shown you way to animate the constraints in one way. Let's have that additional gradational animation value as a constraint. I mean the parameter, additional parameter. To this global parameter set. All right. Okay, I guess that is good for all for today. I think it's spent too much time, I guess. Maybe for people who want to watch back again, it's too many tryouts, too many coding or stuff. So I'm gonna stop right here. But yeah, you could try out the setup I created. As always, I'm gonna upload the files to a GitHub, and you could download the file from the video description page. I'm gonna paste the URL later. You could also download the file from the Patreon page myself, so you could also do that. So this is it. It's free to download, free to use for any purpose, so please feel free to use it for your project. Okay, and I hope it helps you understand some of the things that I did. Remeshing, changing constraints and so on. And hope you find it interesting. Okay. Thank you, Goksh, for a comment. Thanks for watching. I'm gonna end the live now, but if you have any comments, you can leave the comments on the video page. Okay, that's it. Thank you very much, and good night. I will try to do something different next week with different topic. Alright. Good night, and have a good day to you all.